open this computer.
Recording in progress.
Yikes, it's loud. And now I'll share. Thank you. Sorry. So hopefully you all got this, and I won't try to repeat that. If you have any questions about it, let me know. But it's basically a nomenclature thing. This is sort of the way you would write it down. You might write, let me do one more example here. You might, a pen thing. Got to turn on the pen. Okay, maybe you could write one and then in parentheses, plus and minus 0.2 times 10 to the 5th. Maybe that would also make it clearer. But they both have to have the same units. It doesn't make sense that your error is 20,000 times bigger or whatever it is than the number you're measuring. Okay, so C, which I started looking up and then didn't actually finish. Yeah, it's 1 over u squared. Okay, and so this is actually u to the minus 2. And the rule is, so that's curious. The rule is, let's erase that stuff. That weird. The rule is if I take, oh, for goodness sakes. If I take the partial of u to the minus 2 with respect to u, because that's what we're interested in, this is going to be the error in x squared is equal to the error in u squared times the partial of x with respect to u squared. This will be minus 2 times u to the minus 3. The rule is you take 1 away from the exponential term, and you bring this term down in front, and then you have a number 1 smaller. Okay, so if this had been u squared, not u to the minus 2, this would have been 2 times u, because minus 1 from 2 is 1. Okay, so in this case, it's minus 2 divided by u cubed, where the u cubed is now in the denominator. So when I plug this in over here, I get minus 2 over u cubed squared. And so I get minus 2 squared is 4. The error in u squared divided by u to the 6th power, because the square of u third is 6. And this is all equal to ux squared. But then you can just take the square root of both sides. And ux is equal to 2 times u sigma u, divided by u cubed. Okay, so it's this rule right here, that it's the partial of u to the n with respect to u is n times u raised to the n minus 1. And if n is a negative number, then it just becomes a bigger negative number. All right. So this also applies let's see what I can do here. I want to stop the pen. Stop the pen. Oh my goodness. Hold on. This, this also applies to functions like one over u plus v, because the partial of u plus v to the -1 with respect to u will be -1 times u plus v to the -2. And then you take the derivative of what's inside the parentheses, and the derivative of what's inside the parentheses is 1. Okay? So the derivative of u plus v, the in parentheses with respect to u, is actually the derivative of u with respect to u plus the derivative of v with respect to u. That's 0. That's 1. And so what you end up with here is -1 over u plus v squared. Okay, and then in this original problem, I think there was a 2 down here. So there were multiple ways of doing this, as you recall. If this was 1/2 times u plus v, which may in fact be what the book intended, I just always misinterpreted it or thought it was this more complicated one. But the partial of this with respect to u is simply 1/2, because it's the partial of 1/2 u. Let's write it down here. It's the partial of 1/2 u plus the partial of 1/2 v with respect to u. There's no function of u up here. That's 0. And this is simply 1/2. And then the other one, the partial with respect to v, will also be 1/2. Okay, so then you can propagate back into this other function. U squared 1/2 plus v squared 1/2, and this is actually 1/2 squared in this equation. Okay, so it ends up being 1/4 times the error squared here is equal to this. That may be a point where you can stop. Okay, for this simple one. For the more complicated one, you end up with a more complicated function that you then have to propagate into the sum, and you have to repeat this for the v term and the u term. A number of you also, if it was a single function, like this, there's no reason to take a derivative with respect to v. Okay, there's no reason to take a derivative with respect to v because there's no v in the parameter. Everything with respect to v is necessarily 0 because there's no parameter named v in the function. So a number of you tried to force it into a formula that had 2 parameters. When it has 1 parameter, it has 1 parameter. Okay. So obviously you're a little bit out of practice with some algebra and calculus, mostly the calculus functions, which is why I give you these assignments. Okay. So I'm still grading this because I just got the last one and I was working on something else. So I'll finish grading this after we lecture this morning, and then I'll put it in your mailboxes. And obviously, everything that you got wrong, you should go back and repeat and return it in. Okay? Are there any questions about that? I'm not gonna save that. Okay. So here's where we are. We're here, and I posted this out on Canvas yesterday, I'm pretty sure. Am I right about that? Should be this one. Yeah, here's a PowerPoint. So it should be this PowerPoint. I don't think I made any change to it since then. I'll post the version that I now write on when we're done. Okay, and then there's an assignment out here. We'll talk about this at the end. Module. Okay, and so what we're doing today, oh, it's here. No. Well, where did I put it? Did I erase it? Oh, I think I buried it. Sorry. I think I closed it. Sorry. So what we're doing is this chapter 2 coming from this 3-author book. And that's what the top of it should look like. That's posted out there on Canvas as well. Okay, and so what this chapter is an introduction to thermodynamics, and it essentially goes through the first and second law. Okay, and so if we need something, I'll come back over here. And so let me just go here, there. So what we're going to do is we're going to go through more or less what's in this chapter. I basically constructed a PowerPoint that sort of steals a lot of the text or a lot of the equations, and we'll just basically go through that the way that the chapter goes through that, and you should pay attention to that. Okay, and so we're going to essentially start with the concept of the first law of thermodynamics, which is conservation of energy. And it involves either heat or work, okay? And so the nomenclature that we have to get used to up front is the idea that we're talking about systems. And these systems in general will be what are called open or closed systems, meaning that they exchange or don't exchange substances with the surroundings. Okay, and it could be exchanging mass or it could be exchanging heat. Adiabatic means that there is no exchange of heat. Okay, so the system is basically closed. So you can think about this as a beaker or a test tube or a cell or an organism. Okay, and so the system that we're going to talk about is the stuff that's contained in the structure that we're concerned with. Okay, a solution in a cuvette that we're doing experiments on, a solution in a device that we're making measurements on, or a test tube, or a cell culture, or as I say, an organism. Okay, open or closed. Adiabatic means no exchange of heat. Okay, and so it could be something that's got an isolated wall that doesn't allow exchange of heat outside the wall. The state of the system refers to properties that define what the system is. Okay, so the state of the system, and we generally end up wanting to know what the state of the system is at equilibrium, and so we want to know how to reproduce that state and how to define that state. And so what we end up specifying are things like the temperature, the pressure, the volume. I think in the book, just going to let me write here, in the book they might talk about the number of moles, things like this. Okay, we might talk about later on things like partial specific volume instead of just the volume. We'll talk about that next week. Okay, these properties are therefore referred to as extensive or intensive. Okay, and what that is meaning is basically, do they require you specify the number of moles or the amount of material? So for example, the volume tells you something about how much. Okay, and the number of moles, N sub I, tells you how much. Whereas the temperature is the temperature. It doesn't really matter how big the system is. The temperature defines the temperature for everything in that particular system. Likewise, the pressure defines everything in that system. The partial specific volume tells you something about the property volume per amount. It's usually volume per gram. And so it also is independent. So extensive versus intensive. Is it an internal property, temperature, pressure? Is it an extensive property, volume, numbers of moles? As I think I said earlier, thermodynamics is generally concerned with changes, okay? So it's generally concerned with changes between state 1 and state 2, and we'll eventually start specifying this as state 1 to state 2. And so when we start talking about changes in a property, like changes in internal energy, then we'll do E2 minus E1 to define that. Initial minus to final. So the way we do the delta is final minus initial, what the change was, okay? And we talk about these, we prefer to talk about stuff as reversible, and we'll get into that and what that means a little bit. But many changes can be irreversible. That will come up in some of the problems, I think. So generally you want to ask the question, reversible means that we're always in equilibrium through the process. Irreversible means that we're not necessarily in equilibrium at all, we're just making a change. If I expand a volume from V1 to V2 against some external pressure, and I just go V1 to V2, pressure of 1 atmosphere, that's an irreversible change usually. All right. If I do it so that the pressure on the volume keeps something constant so that there's always an equilibrium going on, it's like a piston that is being pushed as the volume expands, then that might be a reversible process. Okay. Now, during these changes of state is the way we're going to describe these, because the internal energy will eventually be described as a state function. We can do a couple of things. And the simplest thing that we can talk about is that energy is transferred into or out due to a temperature difference. So are we going to change the temperature? Are we going to go from T1 to T2? Okay, so there's a heat transfer. Or we can also do work. We can do an exchange of energy between a system and its surroundings. There could be a volume change against some external, I say volume there, I bet you that's supposed to say pressure. Okay, if we go back to the text, I'm suspecting I said that wrong. There could be a change in surface area against a surface tension. This will come up later in the course now, because I'm going to do a lecture on liquid-liquid changes of phase. So where you make a phase change, and the thing that you're doing when you make a phase change in that context is you're creating a cavity that then grows as you add more mass to it. And one of the biggest things that you're doing when you do that is you're creating a surface between the droplet and the bulk solution. And that's a change in surface area, and it takes energy. Or we could do something like electric work, okay? So we're going to define a function involving the first law, that is the change in heat and the change in work, okay? And for all intensive purposes, under the experimental simple way that we're thinking about this, that's all you can basically do. Either you're exchanging heat or you're exchanging work. And the heat can be into or out, and the work could be done on the system or done on the surroundings. So the signs of those things will depend on which direction things go. So there'll be a function that we're now going to define called internal energy. We will use this symbol E that I just used above. And the energy that we're normally talking about, okay, are things that we want to talk about molecularly because we're interested in molecules. If we were doing a different kind of thermodynamics course, we might be talking about energy, engines, a heat pump of some kind, something that is going through a cycle, taking heat from one place and putting it in another place. So we might be bringing heat in from solutions that are being directed into the ground, and I may be grabbing heat from underneath, or we might be pumping heat out of a room to cool it, okay? We're not talking about that from this for this course because we're really interested in molecules, and that's where this will primarily, not entirely, focus. And so internal energy refers to things like translational, vibrational, rotational energy. It will refer to chemical bonding. It will refer to non-bonding, or what we have been calling non-covalent interactions, as discussed in a table coming up and in chapter 4 of Creighton. And then in a second, we'll get to this definition of the enthalpy down below. So let's talk about these non-bonding interactions first, or the non-covalent interactions first. So last week when I was talking about this to you, we talked about Coulomb's law. We talked about a form of the equation that involved a dielectric constant and said that varied over a wide range depending on the solution. Was it water or alcohol or something? And then I introduced the idea that's developed in Creighton that we might also have dipoles. And we might have permanent dipoles, we might have induced dipoles. And so the interactions that occur are not just between charged spheres or charged points, but they also might be interactions between dipoles, okay? And what it said in Creighton, without going into all the details, was that ion dipole or dipole-dipole or induced dipole-ion or induced dipole interactions obeyed different radial dependencies. And you will recall from Creighton that they said third, fourth, sixth. And the language presumably matched up. So if there's an interaction between ions, the energy equation goes as the first power. If there's an interaction between ions and dipoles, then it goes as r squared. If it's dipole-dipole, it's r cubed. Okay, without specifying initially that this also involves the orientation of the dipoles. If it's ion-induced dipoles, in other words, the ion induces charge to be redistributed within a molecule, and therefore it's an induced dipole, it's not a permanent dipole, it'll go as r to the fourth. And then if you have induced dipole interactions, these are known as dispersion forces. They're also known as London dispersion forces. This goes as r to the sixth, okay? And so this describes in a lot more detail the nature of the interactions that might be going in the molecules that we're talking about, all right? And so these are the functional forms of those equations. And you can see those here as kilojoules per mole. You can see there's a wide range of interactions that can occur. They can be very small, they can be relatively large, etc. Okay. All right, now I copy pasted this out of some website that I found. Goodness, there we go. Just to give you a bigger overview of what we're deriving. And other textbooks, other chemistry thermodynamic discussions would do this in a slightly different way. But I wanted to give you this overview so you can put this into a context. So the first law of thermodynamics is the conservation of energy, and we're about to talk about that, okay, involving heat and work. Okay, so the first law of thermodynamics states when energy passes in and out of a system as work, heat, exchange of material, the system's internal energy changes in according to the conservation of energy. So conservation of energy means it's got to be accounted for. The math has to add up, okay? It goes somewhere, all right? The Zeroth Law, which precedes this and is usually not discussed, is sort of implicit in a lot of what we're talking about for reversible processes, that stuff in thermal equilibria has the same temperature, okay? And if you're therefore in equilibrium with something else, then it's in equilibrium with the thing you're in equilibrium with. So this is sort of a temperature thing. The second law, as you're going to see, involves entropies, okay? And it states in a natural thermodynamic process, the sum of the entropies of the interacting system never decreases. Another form of the statement is that heat does not spontaneously pass from a colder body to a warmer body, okay? Another way that this is often stated is the entropy in an isolated system always increases, okay? Systems do not spontaneously order themselves. We will come back to this when we talk about, for example, the condensates that I'm going to give you a lecture on later and what that order means. We could talk about this in terms of the Earth, okay? There's order in the Earth, although there's a lot of disorder and disharmony in the Earth, but there's a lot of order in the Earth, okay? But it costs energy to make it happen. You might have order in a cell culture, but it costs energy to make it happen, okay? So it just does spontaneously order itself. There's a cost. And one of the costs is that the entropy must necessarily increase. And then the third law, which is something that we will not talk very much about, but the third law basically is you cannot reach absolute zero. A system's entropy approaches a constant value as the temperature approaches absolute zero. With the exception of non-crystalline glasses, the entropy of a system at absolute zero is typically close to zero, but it can never be zero. Okay? The reason for that is there's always some disorder. You can never have a perfect crystal, a perfect organization. And consequently, that leads to an elevation in temperature. Okay, so the first law is conservation of energy. The second law is entropy must increase. The third law has to do with absolute zero. Okay, that's a general overview that a lot of books and a lot of courses often get into. All right, so this is a condensed version of what's in the beginning of this chapter. And it has to do with conservation of energy. Okay, so delta E is equal to Q minus W. Heat absorbed and work done are defined as positive. Okay, so the result here depends upon, is the heat absorbed or is the heat released? Is the heat positive or negative? Is work done on the system or is work done by the system? Okay, all right, and so the signs matter in that context. Now the nomenclature here, delta E, is this nomenclature having to do with the state function. And the nomenclature has to do with this E2 minus E1 nomenclature that I used, okay? And it has to do with a path. And the reason that E is a state function is because it's path independent. It doesn't matter how you went from state 1 to state 2, the internal energy change will be the same, okay? So it's a state function because it's path independent. We can then interpret this in terms of a derivative, dE, okay, which, as it says in the text here, is independent of the path. However, the dq with a bar through it and the dw are path dependent. That's a little bit of a contradiction, a little bit to get your head around, but it's by definition the way things are. Okay, the dq with a dagger and the dw depend on how you did it. How did you exchange heat? How did you do the work? Remember the example I just gave you that you can expand a volume. It depends on against what. Is it expanding against a vacuum? Is it expanding against a fixed pressure? Is it expanding against a pressure that maintains some kind of an equilibrium? Okay. So this is the general equation for dE, dq minus dw. But then the question is, what is work? And so work could involve volume increases. Okay, so increase in volume against some kind of a pressure. So only changes in volume. Or it could do some kind of electrical work where you move charge across a membrane, for example, in oxidative phosphorylation. We will, generally speaking, neglect stuff like this, and we will primarily talk about changes in volume. The book will occasionally introduce a term that says something like other work. Okay, and it'll give it some kind of a symbol, meaning there might be other kind of work, but we're going to neglect that, and we're going to make the problem easier. Okay. So this equation here and this equation here are sort of the two simplest ways of expressing internal energy. All right. Now we're interested in processes, primarily macromolecular processes, and we want to have some understanding in thermodynamics of what's happening and why it's happening and how it's happening. And so history has led to the derivation of other kinds of state functions. And another state function is called the enthalpy. And back here, I defined it at the bottom. In the book, I think it must do it at this point, and I'll put it in there. The enthalpy is defined as E plus PV. Okay, and so what we're going to do is we're going to insert into dH the E plus PV function. And now we're going to differentiate. And so the derivative of this is dE plus the derivative of PV. The derivative of PV is P times dV plus V times dP. Okay, the derivative of the first times the constant, and then the derivative, excuse me, the derivative of the second term times the constant P, and the derivative of the first term times the constant V. Okay, so this is how you generally differentiate a product. Now we're going to substitute in dE. dE from up above, it'll be dQ minus dW, and we'll still have PdV, and we'll still have VdP. Okay, now work up above is defined as only volume changes. So if only PDV work, then PDV gets substituted for dW, and then we have minus PDV, we have plus PDV, these cancel. So this means that dH is equal to dQ plus VdP. Okay. So this then allows us to make simpler substitutions. Okay. Assume that we're at constant volume. At constant volume, dV, where is it? It's up above here. My pen is not picking up. There it is. dV at constant volume is 0. So down here, dV at constant volume is 0, and therefore all that's left is dE is equal to dQ. The PDV term is 0, constant volume. That's what that means. And those derivatives that you were taking for that chapter, if you don't have a V function, dV is 0. There's no function of V. So it's the same sort of similar here. Constant volume dV is 0. Consequently, one way of describing dE is it's the heat released or absorbed at constant volume. And so it's written as Q sub V. At constant pressure, the enthalpy is also just dQ, because the enthalpy is equal to dQ plus VdP. At constant pressure, dP is 0. So dQ is equal to constant pressure heat. Okay. So that sort of simplifies what heat means in terms of the state of the system. At constant volume, dE is heat. At constant pressure, dQ is heat. Okay. Now the book says what I've summarized down below. In most of biology, in vivo, we're working at constant pressure. You and I are now sitting in a constant pressure environment. Our solutions sitting in a test tube are generally speaking at constant pressure. Okay. Consequently, when we talk about heat, we're talking about the enthalpy coming from constant pressure. However, most volume changes during whatever process we are talking about are pretty small. If we change the temperature by some temperature, even going from 4 degrees to 37 degrees, the volume is generally a small number. It's not 0, but it's small. And so the enthalpy and the free energy and the enthalpy are generally close to one another. The book describes it as approximately equal to one another. Okay, we're going to look at a summary in a second. All right, but generally speaking, these are the general concepts that the book is trying to convey to you. Okay, so this chapter has some nice summaries of everything that I just went through. Okay, and I split this up in this way because it's small. It's probably small even here. So the flow of this is dE is dQ minus dW, path-independent, path-dependent processes. If it's adiabatic, Q is 0. There's no exchange in heat, so dE is minus dW. If it's an isolated system, then it can't interact with the surroundings, so it can't do work on the surroundings, and so dE is 0. Okay, that's sort of a generalization. If you're not adiabatic, you can divide the work into two kinds, and I mentioned this back a bit. There's PDV work, volume change work, and everything else. And everything else is summarized as this dW prime. Okay. If you include that, then you get 3 terms: dQ minus PDV minus dW prime. And I don't know that the prime is there. There's supposed to be a prime. I see the prime there. Okay. If it's only PDV work, then that prime term drops out. If it's a constant volume, then you get this Q sub V term. All right. If it's a constant volume, then the PDV term goes to 0 and you have these 2 terms. If you add something to both sides, so this is manipulating it to come up with the definition of enthalpy. If you add VdP to both sides, then this essentially gives you the definition of the enthalpy, because the enthalpy is E plus PV. So adding VdP to both sides gets you dE plus PDV. They've taken PDV to the left, and plus VdP. So this ends up being the derivative of H, and that ends up being what it's equal to on the right. So this term ends up being a definition of H, and it defines, therefore, that dH is going to be dQ minus other work plus this VdP term. And then again, constant pressure, this term goes to 0. And so it's dq minus dw. Adiabatic, no exchange of heat allowed, only other work. No other work, only PDV. Then the dq is equal to the qp. And only PDV work, adiabatic, there's no heat exchange, then dE is going to be 0. So these seem like sort of trivial and easy to follow transitions, and that's sort of how it's meant, so that you become familiar with this. Questions that are usually like this allow you to eliminate stuff. Isolated, dE is equal to 0. No PDV work, dV is 0, and it has consequences. There's another summary like this later that we'll go to. Okay. Now, that's the first law. You can account for all of the internal energy by changes in heat or work, and then you can break work up into various kinds of things. All right. What about the entropy? Okay. And this revives something that I lectured on to you, maybe in a disorganized way, about one of the ways of talking about distribution of energy, or sum over states is the way it's often said, or counting the ways is the way it is sometimes said, okay? And it's usually introduced with this parameter called W, which gives you a possibility of counting the ways, all right? And I think this problem says that you have various energy levels, 1, 2, 3, 4, 5, 6, E, and you have 6 particles with a total of 10 energy units. How many different ways are there to distribute 6 particles over different levels so that you have a sum of 10? All right. And this is showing you opportunities. Here's 1, 2, 3, 4, 5 plus 5 gives me 10. 1, 2, 3, 4, 5, 6, 7, and then 3, 8, 9, 10, etc. Okay, these are the different ways that you can distribute the energy. All right. What this formula is basically telling you is there are actually 6 permutations that allow you to do this. And those permutations involve swapping positions. This particle moves up here, this particle moves down here. This particle moves up, this particle moves down. And if you do this sort of thing, you end up with 6 positions. This orientation allows you to have 60 permutations, and this is a result of this formula over here. And likewise, this has 15 permutations. So this is a distribution of energy. It's a way of depicting it. And W is one of the formulas that you can use for depicting this. I gave you the example of numbers of students, numbers of chairs, how many different ways are there to distribute the numbers of students between those chairs. This is giving you it in a slightly different way. In general, this is representable by what is called a Boltzmann distribution. The Boltzmann distribution reflects the fact that the number of particles in the state I is equal to the number of particles in state 1 times an exponential of minus alpha is usually a term introduced in general. They immediately start telling you that it means 1 over kT. And then the difference in energy between the levels. So the number of particles in E6 will involve the energy in 6 minus the energy in 1. It'll be the baseline. This will help be a way of hopefully predicting or describing what the distribution looks like. Okay. They introduce immediately other kinds of nomenclature having to do with different ways of defining this. it's possible that you can have states that have similar total energy, but different distributions. And it allows you to express stuff in terms of different kinds of ensembles. So you might think of this as different conformations of a protein. They have similar energy, but they're actually different conformations. And consequently, you have to kind of count over those states in a different way. And so there might be 2, there might be 10, there might be 1,000. And so you define these different states in terms of these substates. Okay, and so you can end up doing this in terms of not just what the distribution is in one state, the Boltzmann distribution in one state, but the Boltzmann distributions in multiple states. When you do this, you can then do a sum over all states. And so notice this term up above that I use. So the total n is essentially equal to the sum over all n sub I. Okay, and that ends up being a sum over all states. I'm going to stop for a second because I want to come back over here and just verify that I didn't make a mistake there. It's the sum term that I was unhappy with. See the n sub I here is equal to this. So what I'm looking at is the way that this is summed. I'm looking at the way the sum, this would be sum over n sub I, so I didn't write this down here. Not happy with this. N is equal to the sum over n sub I. This is n sub I. Okay, so when I take the sum, the g sub I is the only term that's got a subscript I, is inside the sum. And what's taken outside the sum is the n1 term in the g1 term. Okay, so it's, I think, I may not have that right in the other expression. So let's go back to this expression, right? Yeah, I think that's wrong. See this g, n sub I, that expression right there is wrong. That should be a 1, not an I. And then it makes sense that it could come outside the sum. All right. So when I made this, I just put the wrong thing in there. Sometimes in reading those, it's a little bit illegible. And sometimes I don't pay attention. Yeah, and so over here, that's also probably a 1. So n sub I is here. It's g. So n is in the denominator, and this ends up being this term, n1 g1. And n sub I is in the numerator. And again, I think this should be a 1. We'll have to go back and verify that. N sub 1, g sub I, g sub 1, n sub 1, g sub I. And so this one actually may be an I. We'll have to make sure about that. G sub I, G sub I. So I think that looks better. I'm still not happy with it. N sub 1, G sub 1, G sub I, and then that's G sub I. Yeah, that looks G sub I. Yeah, so this one should also be a G sub I. You didn't think I actually was paying attention to this, did you? Okay. And so these are permutations of the same. So this is the Boltzmann distribution for a particular state I. And then this is summed over all states. And so sum over states or sum over all states, this is also eventually in some nomenclatures known as a grand partition function. It has something to do with statistical mechanics and accounting for all of the energy differences in all of the states between different distributions over different ensembles of states. I'm saying a lot of things that maybe don't mean anything to you at this point, but it's basically a way of reflecting how you count and how you account for all of these various states. Ultimately, what we're interested in is talking about this in terms of entropy. Okay, so let's go back to here. Okay. So this section now talks about entropy and will evolve into free energy and equilibrium. So the second law of thermodynamics has something to do with how particles distribute themselves. Okay, you can think of it in terms of Boltzmann's distribution. You can think of it in terms of diffusion outside of a bag of sucrose. You can think about it in terms of expanding something reversibly against the pressure. So what we're doing here is diluting the sucrose solution. We're allowing water to come across the membrane. Sucrose cannot get out of the membrane, so it's expanding, but the pressure is always attempting to be gradually reduced so that you have some kind of an equilibrium between the process. This is a reversible process. This process where the water is simply diffusing in and out is an irreversible process. You cannot easily reverse this process. If you push this piston back down, forcing the water out, you can recover the same solution. So that's why this is reversible and this one is not. Okay, so this is where we introduce a definition. And the definition is the entropy. It's an extensive property because it involves how much. But the definition, the simple definition that is actually written on Boltzmann's grave is that the entropy is equal to Kb, the Boltzmann constant, times the natural logarithm of W. W is what we defined back here for this particular case, okay? And it's an extensive property because if we take the natural logarithm of W1 minus times W2, the logarithm of a product is the sum of the logs, and Kb ln W1 is entropy 1, and Kb ln W2 is entropy 2. And so it's extensive because the entropy of the total is the sum of the parts. Okay, it depends on how much. All right. So if we now want to talk about this in terms of counting the ways, Boltzmann's distributions over levels or states, then we simply plug in the Boltzmann equation to do this. And so we use the W equation defined 2 slides previously, n factorial And you should, I think we talked about this before, you're all familiar with the fact that this is n times n minus 1 times n minus 2, etc., down to 1. Okay, and the same for the n1 factorial, n2, n3, and 4. Okay, so W here is n factorial divided by n1, n2, n3, and n factorial. These 1s, 2s, 3s refer to different levels and different amounts of particles. Okay, so now we're going to take the natural logarithm of this. All right, and so the natural logarithm of a quotient is the difference of the quotients, the terms in the quotient. So the natural log of this is the natural log of n factorial minus the natural log of n1 factorial minus the natural log of n2 factorial, etc. Okay? Now, there's an approximation that always ends up being used here, and it's simply that the logarithm of n factorial can be approximated for large n as n ln n minus n. These must be big numbers to be true. They must be moles of particles, 10 to the something. So therefore, each one of these terms can be approximated in this way. So the logarithm of n factorial is n natural logarithm of n minus n minus the natural logarithm of n1 factorial. So it's a minus the first term, n1 ln n1, and then minus a minus plus n1, etc. Okay? So we can define these as basically recursive relationships. The recursive relationship is that the sum over all n sub I adds up to n. In other words, all of these n1s, 2s, 3s, 4 are numbers, fractions of the total number of particles. So they sum to n. Okay, so the sum over n sub I is equal to n. And we can define, he does this as a space holder, I'm not sure why you need to do this, that n times ln n is equal to k. So you can approximate this because minus n plus n1 plus n2, etc., goes to 0. It goes to 0 because the sum of all of the n sub i's adds up to n, and they have different signs. So all of these particles, all of these numbers go away. And what you're left with is this first term, n over ln n, which is defined as k, and then the sum over n sub 1 ln n1, n sub 2 ln n2. There's a minus sign in front of all of them. So it's the sum over n sub I ln n sub I, where I goes from 1 to whatever the total number is, okay? And the total number might end up being something like n, okay? Goes to some total number. For an infinitesimally small change, which by definition means that it's a reversible change, we can therefore write down that ds is equal to kb times d ln w. So notice what we're doing here. We have a definition of ds, of s, excuse me. Let's write it way over here if I can make the pen work. S is kb ln w. Kb is a constant. So ds is equal to constant times d ln w. Okay, that's what we start with here. So ln w, therefore, is minus kb d n sub I ln n sub I. And notice it's the derivative over the whole term. Now let's go back. This is what we have for ln w, but this first term is n ln n, and this is a known quantity, and it's a fixed quantity. It's the total number of particles. It doesn't change. And so taking the derivative is 0. So the first term, when you take this derivative, is 0. The second term is the derivative of this term. Here's the minus sign, and then you're taking the derivative of this sum. Okay, and so that's why you get this term. It's minus KB, the derivative of the sum. Okay, and so it's the derivative of the sum of a product. So it's minus KB, the first term, the sum over the first term times the derivative of the second term, minus KB, the sum over the second term times the derivative of the first term. So it's the derivative of two terms. AB is A times DB plus B times DA, okay? The derivative of that first term that I told you on the previous slide is 0. The derivative of this term, because the number of particles are constant, and that comes from the fact that this is the sum over n sub I times d ln n sub I. Sorry, I'm skipping a step. And this is what you use in that problem set on the free energy. So this is the derivative of ln n sub I, but this is equal to dn sub I over n sub I. That's because the derivative of ln x is equal to dx over x. So the derivative of dln n sub I is dn sub I divided by n sub I. These terms now cancel, and it's the sum over dn sub I. But the sum over dn sub I is the change in the number of particles, because the sum of n sub i's add up to n and they don't change. So this term is 0. Consequently, all that's left is ds is equal to minus, so it's the second term that's left, is d ln n sub I dn sub I. Okay, that's what it is. And then if you plug into this the Boltzmann equation, ln n sub I, you get two terms. The logarithm of a product is the sum of the logs. You get ln n sub I plus ln e raised to the minus epsilon over kt. So you get ln n sub I. The natural logarithm of e is basically just the exponential. It's the inverse function. And so you get the delta epsilons over kt. Okay? And so you can plug this into the definition up above. So now I'm slowing down to make sure I'm catching up with my own math. This first term so the first term, so this gets broken up. I'm sorry. This gets broken up. This term, they're showing you here what this term adds up to. Okay. But then when you plug it into the sum, okay, the first term ends up being This ends up being two terms because I just showed you it's two terms. The first term ends up being KB sum over stop. Stop it. ln n sub 1 dn sub I. That's a constant, and this is the sum over dn sub I. And again, the number of particles is constant, and so this first term goes to 0. All you have is the second term. The second term is minus delta E over KB. And so the second term will be KB minus a minus, and then you'll get this delta E over KT times dn sub I. So this makes two terms. The first term goes to 0. And you can simplify this taking temperature outside. The K's cancel, and you get 1 over T is the sum over delta E dn sub I. Okay. So these are energy differences. All right. These are energy differences, and they correspond to transitions in energy between levels, which essentially means changes in or motion of heat. Infinitesimal, small, reversible changes. And so we're going to call this heat exchanges that are reversible. And so this term ends up being approximated or defined as dq reversible. Okay. There's no work going on here. You're simply moving dynamics, you're moving vibrations, you're moving sources of internal energy around, and it ends up being the changes in the reversible heat in the system, which we can approximate as Q reversible. And then there's this nomenclature change that we like to make, going from a delta S in terms of heat, reversible divided by T, or ds is dq divided by T. Okay, and so this is sort of a summary of what entropy ends up being. Now notice where we came from. We came from this sort of Boltzmann's distribution picture of energy states, sums over states, moving particles around, changing vibrational states of particles, thinking about this as being a reversible process potentially. We express this in terms of W's or states and summing over various states using this W function, then define the entropy here as ln W, and then took the derivatives in a certain order to get us to this simplification that the change in entropy is essentially dq divided by T. Okay. So entropy is also a state function. Again, going from state 1 to state 2 does not depend upon the path, generally speaking, but the work done or the heat done is path dependent. And this is showing an example of how you might calculate isothermal reversible expansion, 1 mole of gas, 1 mole of an ideal gas going from V1 to V2. Okay, this dq is therefore equal to dw. Why is that? If you go all the way back to the expression we talked about earlier, ideal gas means there's no interaction between particles, and therefore expansion going from V1 to V2 has no change in the internal energy, and it's necessarily 0. Okay, so the internal energy of an ideal gas, ideal means no interactions. The equation for an ideal gas, PV equals nRT, defines a state where the particles have no volume and have no interactions. So consequently, dq must be equal to dw. dw involves only volume change, so it's PDV work. If it's PDV work, then I'm taking the derivative of both the left and the right. The number of particles does not change. Let's assume it's 1 mole, so N equals 1. Okay, so it's RT, isothermal temperature constant. PDV nRT. Okay, so I've defined this here. Okay. So rearranging this equation, P is equal to RT over V. Okay, and so P dV is equal to RT dV over V. That's where this comes from. All right. So the amount of heat is the integrated across the volume change going from V1 to V2. It's RT divided by T, because we're trying to solve essentially here for the entropy now. So we'll take dQ divided by T. So it's this whole expression divided by T is the integral of dV over V. Okay. And so this ends up being what you should remember. The derivative of ln V is 1 over V dV. So if you have dV over V, the integral of 1 over V dV is d ln V. So it's the integral. So it ends up being RT over T ln V calculated from V1 to V2. Calculated from ln V minus ln V2 minus ln V1. Okay, which can be expressed as ln V2 over V1, which is the final answer. The T's cancel. The T's cancel. And so you get R ln V2 over V1. Okay. So the entropy change for an isothermal reversible expansion is R ln V2 over V1. This is expansion. V2 is bigger than V1. The natural logarithm for this process is positive. The entropy increases. It's positive. The delta S is positive, increasing in an expansion. Okay. They do this in the book in a more statistical way. If you divide the volumes into particle distributions, you divide it into N1 cells of volume V, where V is some small volume that sums up to V1. So that V1 is the number of particles N1 times this small volume V. I should probably have made this a small v. And then you divide the larger volume into N2 cells of the same small volume, such that V2 is N2 V2. Then we essentially have a way of putting molecules into cells, one molecule N1 ways. So one molecule can put into N1 cells N1 ways. It means there are N1 cells I can distribute that one particle N1 ways. But then I have a second molecule, and I can put that second molecule in those same volume elements. And so it's the product of N1 times N1. And if I have multiple numbers of particles, every time I distribute them, all those particles can sit into any volume element. So the number of ways of distributing them is n1 raised to the nth power, and I mean that to be Avogadro's number. I could not find a function for Avogadro's number. It would normally look something like that. Okay. So this is the number of ways of distributing particles in V2 and in V1. And consequently, the final state and the initial states look like this, because remember, delta S is KB times the natural logarithm of W. But W here equals n1 raised to the nth power. Okay, so it's n2 raised to the n, the final state, minus n1 raised to the n, the initial state. You can combine logarithms. The difference in the log is the quotient. So it's kb ln n2 over n1 raised to the nth power. All right. When you take the logarithm of something raised to a power, the n can be brought down in front. This n can go down in front. So this is equivalent to n times kb times the natural logarithm of n2 over n1, numbers of cells. All right. This, you may or may not know, is the gas constant, R. The gas constant is defined as Avogadro's number times Boltzmann's constant. So we can rewrite this now as R ln n2 over n1. But these numbers correspond to V2 divided by this small volume element. Remember, we broke this volume element, this volume V2 up into a small volume element. And that gives us the total number of particles. Okay, and so it's equivalent to this. It was defined on the, oh, here it is. It's right here. I'm sorry. So it's N1 is equal to V1 over V. So we're substituting here. The volume element that we broke things up to is constant, so the same, so they cancel. And this is V2 over V1. But look, it's the same. It's the same as this previous derivation here. Here we defined it as a volume of an ideal gas, and we put in the ideal gas law. And we ended up with an equation for delta S in terms of R and the ratio of the volumes. Here, we did it in terms of distributing particles and how to distribute particles. There's no discussion here of pressure and temperature, okay? And volume. It's basic, we substitute volume at the end to get to here, but we end up with a similar expression that the entropy change is equal to K times the natural logarithm. Oh, I did this substitution here and I threw out the R. So these probably should be R. That's probably a mistake on my part. Times the natural logarithm of V2 over V1. Again, V2 is bigger than V1. The entropy change is increasing. It's positive. All right. And then they go through a very quick sort of word explanation for the same idea in that right side of the figure up above, where you're letting water in and diluting the sucrose solution. And when you do that, you end up with the inverse concentration because as you expand the volume, the concentration becomes more dilute and things end up being inverted. And so, and again, I bet you this is supposed to be an R. We'll go back and look at that. But this also ends up being a positive number because the initial concentration is higher than the final concentration. So again, the entropy change is positive. That's where we got the original expression. Here's where we're doing a PDV. There's an R term. There's an R term here. So somewhere along here, there's where I transferred, and then I made a mistake all the way along using KB instead of R. So all of those expressions should be R. Okay. And then they go on to do something called the entropy of mixing. Assume there are n components with n sub I molecules each, and a total, therefore, of n0 numbers of particles. So that should be a subscript I. Total number of molecules the same size so that each occupies a cell of the same volume. The total number of cells would be n0, the total number of molecules. So we're doing this cell problem again, and we're going to do this mixing problem. And what we're doing is we're going to take pure components, n sub i's, and mix them together. So we have a total of n0 molecules. So the entropy of mixing will be the entropy of the solution, the mixture, minus the entropy of the pure components. We are only concerned with mixing. We're talking about no interactions at this point, so we can think of this as ideal components. And we're really only interested in distributions again. And again, I've made this mistake all the way through. That's terrible. No, maybe this is okay here. Well, we'll go back and double check. You need to go back and double check that I'm doing this right. Okay, so therefore the entropy of mixing can be written down as the definition. It'll be the numbers of ways for solution and the numbers of ways for pure components. And it'll be divided because it's the natural logarithm of a difference is the natural logarithm of the quotient. The pure components, there's only one way of distributing because every component is the same and you can't tell them apart. So there's only one way of distributing pure components into some kind of grid, because that's what this essentially is. The delta SM for the solution is ln W solution. W is a number of ways of arranging N0, this should be a subscript 0, into groups with N1, N2 types, and these all should be subscripted. I think at this point that maybe they use capital N's here, okay? And so it ends up being the same derivation essentially. You then use Stirling's approximation. You take the first term as the NW term and then minus each of the other terms, the N, ln N minus N sort of terms. The sum over all the N terms adds up to N0 and the signs are different so that they cancel. Okay, and then you end up with the first term, which previously we called K, and then we end up with this second term. Yeah, here, maybe in this particular case, the KB might be correct. The N comes out of a subsequent step. So this term is going to involve breaking this up into, oh, they're putting, I'm sorry, that doesn't go to 0. That doesn't go to 0. That N sub 0 becomes the sum over N sub i's, and that ends up being equal to 0. And then this sum over N sub i's is taken in front and multiplied by the difference in the logarithms, which becomes the quotient, N sub I over N sub 0. Notice this is 0 over N sub I, but the sign is taken outside to flip these and a sign change. So it ends up being the sum over N sub I times the natural logarithm of this quotient, and this quotient ends up being mole fraction. The number of molecules of I divided by total. And so this definition is a mole fraction definition. How many total numbers of particles divided by the total number of particles? If you divide both of these by the mole unit, you have numbers of moles, mole fraction. Okay, so multiply and divide by Avogadro's number will get you the mole fraction. And so Sn, the sum n sub I ends up being equal to n0, and that's where the nkb comes from, and so that's where it becomes R. And these become numbers of moles. And so the expression is minus R sum over n sub I is ln x sub I. So that's where you get the R. They must say this. I put the R in here already. So that may be a step. This may actually be KB, and it's times n, and that's where the R comes from. This says the entropy of mixing is greater than pure components without interaction, since all mole fractions are less than 1, and their logs are negative, and we have a negative sign. So the entropy of mixing is always going to be positive. There's a break here in the text. Let's go back to the break. So can I make this transition smoothly? There's an entropy here, a break in there's the volume, there's the distributions of particles, there's the expression. This also has the R there. That I'm now confused. There's KB, and down here it's R. That may be a typo. Between one of us, there's a typo there. That may actually be minus R ln x sub I, because this may give you n0 times KB. Notice up above the KB. So that may be their mistake, not my mistake. Okay, they transition here in the text to talking about melting. And they start talking about melting in terms of heat being transferred within a crystal that transitions a regular structure that transitions to a non-random structure. So this is equivalent to denaturation. So it becomes more random, and it has higher entropy. So the entropy change can be written down in the traditional way. And I think this is a typo here as well. I think that's an equal sign. Is Q, remember Q reversible, or Q at constant pressure, is equal to enthalpy divided by the temperature at which the enthalpy occurs. Okay, and so that's what I have back here. And then down below, we do this in a slightly different way because we ask, where does Q come from? It may be easier for me to do it this way. Where does this go? So they talk about this enthalpy change in terms of heat capacity. And so CP is a constant pressure heat capacity. It's the amount of energy that it takes to raise the temperature of a substance by 1 degree, okay? And so dQ is equal to that heat capacity times the change in temperature. the amount of energy it takes to raise the temperature by 1 degree times the change in temperature. And so when you integrate this function, it looks familiar. It ends up having this, the integral of dt over t is the natural logarithm evaluated between t1 and t2, and that's why you get this quotient times Cp. This particular example assumes that the heat capacity is constant. So for water, generally speaking, the amount of energy it takes is constant, whether you're at 4 degrees or 90 degrees. This is generally not true for most substances, especially solids. Okay, so there are usually formulas that define this. Okay, so let's go back over here. That's that same point in the derivation. So what we've done is we've derived an expression for entropy in terms of Q and T. And then we've manipulated this derivation of entropy in terms of counting, in terms of distributions of particles, in terms of volume changes, etc. We've introduced it in terms of heat capacity, etc. But then we transitioned back to this general expression. And this general expression is dE is equal to dQ minus dW. But we have been using the expression that entropy, you want me to use a pen here, don't you? Entropy involves dQ over T, or in other words, dQ is equal to T delta S. Okay, and so dE is equal to dQ minus dW. If we make this substitution, we get TdS. And if we assume only volume change, we get PDV. All right. So remember what I said, that E and S are state functions, and they depend upon these variables like temperature, pressure, volume, that define the state of the system. So if we were interested in an entropy change for a reversible process, and if we did this entropy change at constant volume and at constant internal energy, then the entropy would be equal to 0 under these conditions. Okay. The entropy change would be equal to 0 under these conditions. Okay. This term is 0. This term is 0. dE is 0. dV is 0. So therefore, the entropy change must be 0. We went through this a couple of times, and maybe we need to go through it again. When the derivative of something is 0, that means it's at a minima or at a maxima. And it turns out that entropy under these conditions is at a maximum. The second law, an isolated system will approach a state of maximum randomness. Okay, so this is sort of tying together mathematics and molecular parameters and manipulating sort of the derivative functions that we've been working with. Okay, where are we? So it's at this point that they sort of speed up, and other textbooks would slow down at this point and expand. We've already introduced E as a state function. We've already introduced enthalpy as a state function. with some variables. We want to define some new state functions, okay? And we want to ask what those appropriate variables are. So we defined enthalpy previously as these two terms So we've defined entropy, internal energy this way, TdS minus PdV. Remember, this was the Q term and the W term. We define free energy now as H minus TS. So it's dG will now be dH minus TdS minus SdT. Okay. The enthalpy is dE plus PV. So you get a dE, or excuse me, it's not, you get a dE, a VDP, a PDV, and then the two other terms that came out of the free energy. dG must be dH, well, it's right here, sorry, minus TdS minus SdT. And that's where these terms come from. When you do this, and you substitute in this expression for E, TdS added to this cancels, PDV added to this cancels, and you're left with VDP and SdT. VDP and SdT. So free energy is defined in terms of temperature and pressure. And when free energy changes zero, this will correspond to some kind of a minima. And that will be the equilibrium state for free energy. There's another function that the book describes in terms of Helmholtz function. It's defined this way and it has consequences. I'm not going to go over that in interest of time. It will have constant temperature, constant volume as its standard state condition. So this is all derived in this flow chart here in the book, which may be clearer. Over here, maybe not. It's this equation, this down here. That is a little bit clearer. So if you go down here, you can see where the substitutions are made and what the final consequence of this is. So it's helping you sort of get through this distribution. All right. And this is figure 2.4. So then the chapter takes a transition to molecules and molecular behavior and thinking about denaturation of a protein. And it ends up defining this in terms of the free energy of denaturation is equal to the enthalpy of denaturation minus T delta S of denaturation. And it justifies this sort of discussion because it says that the change in the entropy must be positive since we're going to a denatured state from a native state. And the native state, generally speaking, has one folded form or a small number of folded forms, whereas the denatured state has a large number of folded forms. And then we expect the enthalpy to also be positive because we're breaking all of those favorable interactions in the native state. So based on this equation 250, at low temperature, we expect delta G to be positive. Okay. And we expect it to be positive because the small temperature makes the enthalpy bigger than this term. At high temperature, this term becomes bigger than delta H, so it favors an unfolding event because delta G is less than 0. Okay, so this is introducing something that you already know, and I don't think it's sort of developed real clearly here. Or maybe I'm not developing it clearly. That if free energy is greater than 0, this is unfavorable. If delta G is less than 0, this is favorable. And so that's what this is describing. In other words, proteins denature at high temperature. That's sort of what the justification for this is. So the native state is stable at low temperature, and it denatures at high temperature. That's the whole justification for this. Now I've added something here that is not in your text. And what I've added is that there's something called cold denaturation. Cold denaturation is literally when you lower the temperature, some proteins denature. We're going to cover this paper later in the course so that you can put this into a bigger context, okay? I'm probably going to have a whole lecture on folding. It's a condensed version of a lot of stuff that's in the literature. Okay. Let's bury this for a second because maybe this goes better here. So the text breaks this up into a similar kind of Boltzmann distribution, but it defines the denatured state and the native state as this ratio. And then it gives you levels or substates, and it says that the native state really only has one or a few substates, and the denatured state has lots of states. Okay, and so it makes a simplification here that there's only a few native states and lots of different denatured states, and it does this with this figure. And then it tries to approximate what's going on here in terms of these W's. And so up above, it makes a substitution for W. And maybe that's clearer in my oh, I see. So it equates these to the W's and it plugs them in for the G's. And then it changes it to an exponential format. And then it combines the exponential formats so that you have a difference in energies and you have a difference in counting the waves. And it converts this, you'll notice, from K to R. And when it does that, it involves N, Avogadro's number. So this is energy per particle, and this is energy per mole. So there's a substitution of N in here to make these things work out. And then it decides that this change in energy, internal energy, can be approximated by an enthalpy. And these changes in states can be approximated by the T delta S term that's derived up above. And so this ratio, N denatured over N native, can be approximated by this delta H minus T delta S, which can be approximated by a delta G. And then it takes the logarithm of both sides, and it calls this an equilibrium constant. The number of the concentration, if you will, of particles in the denatured state by the number of particles in the native state And that becomes an equilibrium constant. And you can equate that to minus G over RT. So the text goes through this in this way at this point. It uses this definition, that should be a capital S, uses these deltas with some kind of a definition of what we mean by a standard state. And we're now describing a standard state as raised to a 0. And then it says that in solution, rather than thinking about gases, we can think about the standard state in terms of a 1 molar concentration of each component. And we can write down approximate formulas for what this means. One of the formulas you can write down is that the free energy is the standard state free energy plus RT ln A, where A is something called activity. Activity essentially is the concentration times something called an activity coefficient, which I can write down here. I think it'll let me write this down if I do this. Activity is concentration times an activity coefficient. Or you can convert this to molar concentrations at low enough concentration, and then you can write it down as the concentration of A. And they point out in the text that this is actually over some standard state, which is 1. 1 molar is the standard state. It deals with taking the logarithms of a unit, a parameter that has units. And so you can write this down as a free energy plus standard state free energy plus RT. And now it wants to convert this to some kind of equilibrium constant. And now we're back to the idea of an equilibrium constant between various general parameters. And so this nomenclature means P1 times P2 times P3. That's what this symbol means. Over R1 times R2 times R3. Some general state for an equilibrium in equilibrium with products. So reactants and products. And so they're trying to come up with a general expression here for standard state expressions. And they're trying to come up with a general expression for an equilibrium constant. At equilibrium, the free energy is 0. So at equilibrium, the standard state free energy can be rearranged here to be equal to minus RTK, and K has this usual definition that I'm trying to define here. Okay. So we've introduced this before, but this is, I think, going to be clearer. And we're running out of time, but this is going to be clearer. If the expression as shown above here is delta G equals minus RT ln K, then you can bring RT to the other side. And then you can resubstitute the delta H minus T delta S. So this is actually 2 terms. And what the expression is doing is equating this to this. All right. And so it's bringing a 1 over R outside. And it's playing with the signs. So this becomes the first term, T delta S over T. So this just becomes delta S over R. And the second term is minus delta H over T. So this is equivalent to delta H over T minus plus delta S over R. And this is ln K is equal to this. All right. So the idea is that if you plot the natural logarithm of the equilibrium constant versus 1 over T, this is essentially a straight line, the equation of a straight line. This is the intercept, and this is the slope term. The slope of this line will be minus delta H over R. I didn't have the R in here. R over S and H over R. The slope will be this term. M is the convention for slope. One of the conventions. So it's often written as the slope of M. So if you can do experiments where you get the equilibrium constant as a function of temperature, and you plot the natural logarithm of the equilibrium constant versus 1 over T, the slope of the line gives you the enthalpy. And once you have the enthalpy, you can use this equation. Remember, G comes from K, minus RT ln K gives you G. So knowing G and knowing enthalpy, you can calculate entropy. So you can get enthalpy entropy out of a plot like this. This is known as a Van Hoff plot. The Van Hoff relationship, this is a Van Hoff plot. The text says that you could also take a derivative with respect to 1 over T. Only one term has 1 over T. So when you do that derivative, you should get minus delta H over R. I think the text has an incorrect T in here because that derivative should cancel. And this is another way of doing the differentiation, and it's showing you that when you do the differentiation with respect to T, you'll get a different form of the equation that we'll talk about later. This will be known as the Van Hoff enthalpy because it comes from a Van Hoff plot. Okay? So look at what it is. It's the derivative of minus delta H over RT with respect to T. This is T to the minus 1. So that minus will come down in front. It'll be a positive. The T will become minus 2, and it'll be T squared. And that's what you get when you take the derivative of ln K, which is the derivative of this form right here. Notice there's no T in this term. So the derivative with respect to temperature of this term is 0 as written. Okay. So we're at time, are we not? Okay, so this is where I am stopping. It goes through the standard state and defines the use of standard states, and we will get into this a little bit more, but the value of having a standard state. So the change is relative to some kind of a standard state. Traditionally, it's usually defined as 1 molar. It doesn't have to be. And then we get into using this expression for minus RT ln K, because when the free energy is 0, this is the equilibrium. And then we get into the Van Hoff derivation in this part of the plot. And it gets us to this plot and the use of these two forms. Primarily, it's this form for a Van Hoff plot. Okay, so that's sort of where we are. And then what happens after this is some discussion of techniques. All right, so you have a class or something at 12 o'clock, right? Are you nodding yes or no? You don't have a class. Okay. I keep getting these notices that there's something coming up. So I didn't get through all of that. This is something that typically happens when I give these lectures, and I don't sort of skip stuff. So I didn't skip much, and I probably won't skip much the next time. So what we'll start with the next time is a series of descriptions of techniques. We'll get into calorimetry as a general discussion. We'll talk about differential scanning calorimetry, which is described here in terms of a sample and a reference. and what the data looks like and how you interpret it. And then we'll get into an isothermal titration experiment, which is defined here, how you do injections and how you interpret the heat that's generated in terms of some kind of a binding curve and how you extract information out of binding curves. So that's sort of where we're going. There's a problem set out there given to you that discusses the problems from the end of the chapter. And so we'll delay doing that. I think this is a Van Hoff plot. This is actually a derivation from this insert in how you derive an equation. So it's actually asking you to derive this equation when you have two competition reactions going on. And then some of the other problems have to do with things in the first part of the set. So if you want to start that, you can start the first couple of problems. You can probably do this on your own, but I won't have it due until the following week. Now, give me some feedback. This way of creating a detailed PowerPoint to go through everything, I can probably go through a lot of this by just going through the chapter, although the chapter often misses stuff. And so I have to remember to go in and put those small things in. That's what I'm doing in the PowerPoint. Hopefully I'm making it clearer. I'm not just making it confusing. Doing the problems are the kind of point of this initially, and making sense of these parameters initially. Next week, once we finish the calorimetry stuff, we'll start another chapter, and that other chapter is already posted out there, which I don't necessarily have here. So you can see the solutions of macromolecules will be there. It changes up a little bit on what it is we're talking about, and it actually rederives some of the stuff that we've been talking about. We start talking about partial derivatives. In partial derivatives, the point is that when you take a derivative, you're taking a derivative with respect to a parameter, but the other parameters are held constant. So it's the difference between a total derivative and a partial derivative. So partial specific volume, how the volume changes when you change the concentration of a particular component. The protein, for example. What's the partial specific volume of a protein? And only the protein. Everything else is held constant. The temperature is constant. The composition of other components are held constant. You'll see where that goes. It then expands this whole discussion, which I haven't necessarily emphasized enough maybe, that we've been talking today about ideal, non-interacting components, internal energy. Non-interacting components in terms of changes in concentration that don't therefore affect interactions between particles when you dilute something. Next week at the end, the second part of the lecture, we'll introduce the idea of non-ideality and how components have non-ideal behavior. The first thing that means is there's volume. They actually occupy a volume. So the ideal gas law doesn't apply. It's not PV equals nRT. Suddenly there has to be a correction for the volume term that takes into account the volume of the particles, because that volume isn't available to them. So it doesn't count in terms of the available volume. Okay, it's not unlike, so you do have a meeting. When I asked you if you have a meeting, speak up, guys. Okay, speak up. All right, goodbye. I'll see you next week. I'll return the, can you not activate your volume, your noise, your sound? Do I have you suppressed somehow? Apparently I do. You can't speak. Do I have to activate you?
We can speak to you now.
Was it because I didn't do it? I guess.
No, sorry, it was user error on my end.
Okay, so it's user error for all of you. All right, go to your meeting. In the future, talk to me.
Yes, sir, thank you.
I'll see you next week. Bye.
Korea.
Yes.
Why is it this echo? Okay, so you said we can resubmit the homeworks from
Yes.
1, 2, 3. That okay.
Yes, you can resubmit homeworks and I'll regrade homeworks that you got wrong that I pointed.
Okay. Okay. Okay.
That I
Thank you
pointed
so
out.
much.
Okay. All right. I'm going now. Bye.